Hello everyone, my name is Lingxin. I'm very glad to have this opportunity to share our work at this conference. The topic of my presentation is how to select spreading factor and bandwidth for 2.4 GHz LoRa Ad-hoc communication from energy consumption perspective. As indicated in the title, our study mainly revolves around the parameters selection and energy consumption of 2.4 GHz LoRa. Then, I'd like to divide my presentation into 4 parts. First, the background and motivation about this research. Second, the model we have proposed. Third, evaluations and results. And last, some conclusions we have got. Firstly, I'd like to introduce the background of our research. LoRa is a new low-rate modulation technology for wireless communication, which uses spread spectral communications to increase the transmission distance. It can meet the needs of low power consumption and long-distance transmission in the meantime, by changing the data read and receiving sensitivity. And this adjustment is achieved by configuring different spreading factor and bandwidth. As we know, the existing LoRa chip mainly operates at the sub-gigahertz frequency band and form a star-topology network by deploying the LoRaWAN standard protocol. However, in 2018, Semtech released a LoRa chipset that operates at the globally available 2.4 GHz frequency band. Compared with sub-gigahertz LoRa technology, it will be more inclined to use self-organizing methods for networking, such as point-to-point communication, multi-hop relay, or ad hoc communication. As the key parameters to be configured during the LoRa application, spreading factor and bandwidth together affect the receiver sensitivity and data rate. Furthermore, affect efficient transmission distance and time on air, and ultimately affect the energy consumption. Based on this, we came up with a question. For the application of a 2.4 GHz LoRa self-organizing network, how can we configure parameters to minimize the communication energy consumption? To address the problem, first, we needed a suitable model which could be used to evaluate the energy consumption of 2.4 GHz LoRa communication. So, we redefined the existing model. The calculation of energy consumption based on radio frequency circuit power (PM) is more suitable for discrete regulation in practical applications. Meanwhile, based on the dynamically adjustable transmission rate in LoRa communication, we use the transmission time to replace the number of bits in the existing model. TOA in the formula is time on air, which represents the air-flying time of the data packet. Here, we use it to represent the transmission time. In this model, PT and PR are generally constants. Spreading factor and bandwidth mainly affect communication energy consumption by manipulating TOA and PM. Then, we will introduce the calculation of TOA and PM respectively. According to the chip's datasheet, we derive the TOA calculation formula for 2.4 GHz LoRa. When the other parameters have been determined, Spreading factor and bandwidth mainly affect time on air through the symbol time, TS. Obviously, with the growth of spreading factor, symbol time will increase exponentially, and bandwidth is the opposite. The transmission power is related to the receiver sensitivity. For the same transmission power, the higher receiver sensitivity, the farther effective transmission distance. By consulting the data manual, we can clearly see that receiver sensitivity increases with the growth of spreading factor and decreases with the growth of bandwidth. Thus, when the transmission distance has been determined, we can find the minimal data transmission power. It is represented by Pk here. However, in practical applications, energy is required not only for data transmission, but also for manipulating the operation of the transmitting module. Therefore, in our evaluation, we analyzed the energy consumption by using the theoretical value and actual value of Pm respectively. Okay, now we move to the part of the evaluation. Firstly, we simulated the node-to-node communication of 2.4 GHz LoRa under the condition of theoretical parameters. We set the transmission distance to 3 km, calculated the minimum transmission power by using different spreading factor and bandwidth. And finally, we obtained the corresponding transmission energy consumptions, as shown in the figure. We can see that the overall trend of transmission energy consumption decreases first and then increases with the growth of spreading factor by using the same bandwidth. It's not difficult to understand. Although the growth of spreading factor leads to an increase in time on air, it also improves the receiver sensitivity, so we can choose a smaller transmission power. It's conducive to reduction of energy consumption on the whole, but as spreading factor continues to increase, the growth of the time on air will lead to an upturn in overall energy consumption. Meanwhile, the overall energy consumption shows a downward trend with the growth of bandwidth by using the same spreading factor. However, when bandwidth takes the minimum of 1625 kHz, the overall energy consumption increases sharply. This is because the receiver sensitivity has a large drop and directly leads to an increase in transmission power consumption. To sum up, under ideal parameter conditions, larger or smaller values of spreading factor and bandwidth are not conducive to reduce power consumption. Correspondingly, we also conducted the evaluation under actual parameter conditions, and the results are shown in the right figure. Obviously, the overall trend of energy consumption is basically consistent with the curve of symbol time. It can be seen that, under actual parameter conditions, the transmission power consumption of LoRa communication is mainly affected by time on air. This is because, in the PM at this time, the energy consumption required for the actual model operation is much greater than which required for the date chains. At this time, the impact of spreading factor and bandwidth on transmission power consumption will not dominate the chain of overall energy consumption. Based on the evaluation of node-to-node communication, we further simulated the ad hoc communication of 2.4 GHz LoRa. We first obtained the spreading factor and bandwidth that minimize the transmission power based on the one-hop transmission distance. Then, we calculated the total energy consumed by all nodes when using different hop counts, and the result is shown in the figure. It's not difficult to see that, under the condition of theoretical parameters, the energy consumption of the network is mildly affected by the transmission power. Therefore, as the number of hops increases, the transmission distance of one hop decreases, and the overall energy consumption of the network also shows a downward trend. However, under actual parameter conditions, the energy consumption required for the operation of the model is still the decisive factor of the overall energy consumption. The increase in nodes will directly lead to the upturn of the overall energy consumption. Comparing the two figures, we have a new question. Under actual parameter conditions, if the one-hop distance continues to increase, the transmission power will grow significantly. So, at this time, what will be the change of the overall energy consumption? Will the operating energy consumption of the node still be the dominant factor in overall energy consumption? To further analyze the influence of distance and hop count on the overall power consumption under the actual parameter conditions, we fixed the communication distance as 10 kilometers. The final result is shown on the right. By comparison, we conclude that as the total transmission distance increases, the operating energy consumption of the model no longer dominates. Reducing the one-hop distance by increasing the number of hops will also help to reduce the overall energy consumption of the network. Finally, we come to the last part, the conclusion. In this part, I will summarize our work. First, we proposed an energy consumption model suitable for discrete adjustment of dynamic read and transmission power. Second, based on model parameters and actual parameters, we analyzed how spreading factor and bandwidth affect energy consumption. Third, according to the analysis, we have drawn some conclusions about configuring 2.4 GHz LoRa parameters in the node-to-node network and ad hoc network, which provides a reference for the application of the 2.4 GHz LoRa self-organizing network. Okay, that's all for my presentation. If you have any questions, please feel free to contact us. Here is our email address. That's all. Thank you.